Tonight, we're going to talk about something that a Nobel Prize-winning physicist has spent decades insisting is true, and that the most powerful telescope ever built may have just started proving. The Big Bang is the foundational event of modern cosmology, the moment when all of space, all of time, and all of matter erupted into existence from a single point, roughly 13.8 billion years ago. It is not a hypothesis in the casual sense. It is supported by the cosmic microwave background radiation, by the large-scale structure of the universe, by the measured abundances of light elements, by Edwin Hubble's observations of galaxies receding in every direction. For most physicists working today, the Big Bang does not represent the beginning of our understanding. It represents the beginning of everything. Full stop. It is the kind of claim that has been tested from so many angles that doubting it feels less like scientific skepticism and more like eccentricity. But Sir Roger Penrose, who received the Nobel Prize in Physics in 2020 for proving with rigorous mathematics that black holes form inevitably from Einstein's equations, not occasionally, not under special conditions, but inevitably, has spent years arguing something that most cosmologists find genuinely difficult to absorb. He says the Big Bang was not a creation event. He says it was a transition, an explosive handoff from a previous universe that had already expanded itself into near-nothingness, and that the James Webb Space Telescope keeps finding objects in the early universe that should not exist if the standard model of that beginning is correct. By the end of tonight, you are going to understand why a growing cascade of Webb discoveries, galaxies that are too massive, black holes that are too large, elements that appeared too early, and an expansion rate that contradicts itself depending on how you measure it, may not be individual puzzles waiting for tidy solutions, but interconnected symptoms of a universe that inherited its structure from something that came before. If that is the kind of question that pulls at you, like and subscribe so you do not lose this one. Let's begin. The instinct to dismiss Penrose is understandable, and if you have it, you are in good company. Most of the physicists who first encountered his cyclic cosmology did not reach for it with open hands. They reached for it the way you reach for something you are not sure you want to touch. And that's because the claim that the Big Bang was not a beginning but a transition, that our universe is one chapter in an infinite sequence of universes, sounds precisely like the kind of thing a person says when they have stopped doing rigorous science and started doing something closer to philosophy, or mythology, or wish fulfillment. It sounds like speculation dressed in technical language. But Penrose is not, primarily, a physicist in the way most people picture physicists. He is a mathematician, and the distinction matters more here than it might seem. Physicists build models of the world and test them against observation. Mathematicians prove things, not probably true, not consistent with the data, not the best available explanation, proved, in the formal sense, yet where the conclusion follows from the premises with the same certainty that 2 + 2 produces 4. That is the tradition Penrose works in, and it is the tradition he was working in when he did the research that earned him the Nobel Prize in Physics in 2020. What he proved, using the tools of topology and differential geometry, was that general relativity does not merely permit the formation of black holes under exotic circumstances. It requires them. Given the right initial conditions, and those conditions are not rare, Einstein's equations do not offer the universe a way out. The mathematics closes off every escape route. A region of sufficient mass and density will collapse into a singularity, a point where the equations themselves break down, and there is no configuration of matter, no physical process, and no arrangement of forces that prevents it. The Nobel Committee did not award him that prize for an elegant suggestion. They awarded it because the proof is airtight. It has been checked, extended, and built upon by generations of researchers, and it has never been overturned. So when Penrose then applies the same mathematical framework, the same topology, the same differential geometry, to the question of what happens at the boundaries of the universe's existence, both at its birth and at its death, the appropriate response is not dismissal. The appropriate response is to follow the argument wherever it goes, carefully, and see whether the reasoning holds. Here is what the reasoning says. The universe is expanding. It has been expanding since the Big Bang, and nothing we currently understand suggests it will stop. over timescales that dwarf the current age of the universe by factors that are genuinely difficult to express in ordinary language, the expansion continues. Stars exhaust their fuel and go dark. Galaxies drift apart until the distance between them is so vast that no light from one could ever reach another. Black holes, the most enduring structures in the cosmos, eventually evaporate through a process called Hawking radiation, bleeding energy back into the void in slow, imperceptible increments across timeframes that make the current age of the universe look like an afternoon. And what is left at the end of all of that is almost nothing, just photons, massless particles of light, racing through an empty void, growing more diffuse with every passing moment, separated by distances so enormous that the universe would feel, yet to any hypothetical observer, indistinguishable from absolute emptiness. That is the death of the universe as the Standard Model describes it. Cold, dark, and dilute beyond any scale we have words for. Now here is where Penrose's insight becomes something you have to sit with. Photons are massless, and because they are massless, they do not experience time in the way that matter does. A particle with mass moves through time. It has a clock, ticking at a rate that depends on its velocity and the gravitational fields around it. But ticking. A photon has no such clock. From the perspective of a photon, no time passes at all between the moment it is emitted and the moment it is absorbed, regardless of how many billions of years an outside observer would measure. This is not a loose analogy, and it is what the mathematics of special relativity actually says. Massless particles exist, in a precise technical sense, outside of time, and because photons are massless, they also carry no meaningful sense of scale. To a particle that does not experience distance as a duration, because it travels at the speed of light and therefore experiences zero elapsed time, the concept of how far apart two things are loses its physical grip. Distance, as a measurable quantity, requires a clock. Without a clock, there is no ruler. What Penrose noticed, and this is the turn that makes conformal cyclic cosmology something other than a story, is that conformal geometry is a branch of mathematics that deals precisely with transformations that preserve angles and relationships between shapes, but that do not preserve distances or sizes. Yet you can shrink something or expand it by any factor you like, and the conformal structure remains the same. Think of a photograph. If you print it at the size of a postage stamp or project it onto the side of a building, every angle between every line in the image stays identical. The spatial relationships between objects are preserved perfectly. What changes is only the scale. Penrose showed that the universe's infinite, diluted, cold endpoint, that vast void of nothing but photons, is conformally equivalent to a compressed, hot, dense beginning, not similar to, not reminiscent of, equivalent to, in the strict mathematical sense, under a conformal transformation. The two states are the same geometry, expressed at different scales, and because the only things that remain in the end state are massless particles that carry no experience of time or distance, nothing in that end state can register the transformation. There is no clock to notice that a rescaling has occurred. There is no ruler to measure the change in size. The universe, stripped down to its final constituents, cannot tell the difference between being infinitely large and being infinitely small. Its endpoint and a new beginning are, in the language of conformal geometry, the same point. This is the core of what Penrose calls conformal cyclic cosmology. Each universe, each eon, in his terminology, expands from a Big Bang, evolves, exhausts itself, and dilutes into a photon-filled void. And that void is mathematically identical to the starting conditions of the next eon's Big Bang, and not metaphorically, not as an approximation. The conformal structure of the end state maps exactly onto the conformal structure of the beginning of the next cycle, and the sequence continues without a first member or a last. It is genuinely beautiful reasoning. The elegance of it is almost unsettling, that the same property of massless particles that makes them timeless is the property that allows the universe to close the loop on itself, that the death of one universe contains, encoded in its geometry, the seeds of the next. It has the feeling of something that ought to be true, but mathematics alone does not make something true. Geometry can be internally consistent and still describe nothing that physically exists. The question that has to be asked, the question that any serious scientist would ask before taking the next step, is whether conformal cyclic cosmology produces predictions that can actually be tested, predictions specific enough that a telescope could look at the sky and either find what the theory demands or fail to find it. And Penrose says it does. He says the evidence is already there, written in the oldest light in the universe, if you know how to read it. And the oldest light in the universe is not a poetic phrase. It is a physical object that telescopes have mapped in extraordinary detail. When cosmologists speak of the cosmic microwave background radiation, they mean the actual photons that were released when the universe cooled enough, roughly 380,000 years after the Big Bang, for electrons and protons to combine into neutral hydrogen atoms for the first time, and in doing so, stop scattering light the way a dense fog scatters the beam of a headlamp. Before that moment, the universe was opaque, a hot, roiling plasma through which no photon could travel in a straight line. After that moment, the universe became transparent, and the light that had been trapped in that fog was released all at once, in every direction, and it has been traveling through expanding space ever since. That was 13 billion years ago. The photons in the cosmic microwave background have been in flight for 13 billion years, carrying with them an imprint of the universe as it was at the moment of their release. And what they show when you map them across the entire sky is something almost perfectly smooth. A temperature field so uniform that the variations from one region to another amount to roughly 1 part in 100,000. That is not a measurement of similarity. That is a measurement of near-perfect uniformity, broken only by the faintest whisper of structure. And Penrose says that if you look carefully at that whisper, if you analyze those tiny temperature variations with enough precision, you can find something that should not be there. In 2010, he published a paper with the Armenian-American astrophysicist Vahey Gurdzadian, presenting what they called Hawking points. The name is deliberate. Stephen Hawking demonstrated theoretically in 1974 that black holes are not perfectly black, that they emit a slow, faint radiation caused by quantum effects near the event horizon, losing mass so gradually that the process takes an almost incomprehensibly long time to complete. But Penrose's argument requires that in a previous eon, black holes did eventually complete that process. They evaporated entirely, and when they did, the enormous energy released in the final stages of that evaporation would have propagated outward through the end of that eon, passed through the conformal transition into our own, and left a mark on the earliest light of our universe. A faint bruise, a slight warming of the cosmic microwave background radiation in a circular region, is centered on the point in our sky that corresponds to where that ancient black hole once was. These circles, Penrose and Gurdzadian reported, are roughly the size of the full moon in the sky, and they found hundreds of them in the data from two of the most precise CMB surveys ever conducted, the Wilkinson Microwave Anisotropy Probe, known as WMAP, and the Planck satellite. Not one or two, hundreds. And Penrose argued that the probability of that many such circles appearing by random chance was less than 1 in 125. That is a number that, in any other context, would be taken seriously. A probability of less than 1 in 125 means that if you ran the universe 125 times under purely random conditions, you would expect to see this pattern arise by accident no more than once. That sounds like signal. That sounds like something real, hiding inside the oldest photograph in existence. A photograph taken when the universe was barely a breath old and has been traveling toward our instruments ever since. The excitement that met this paper was genuine. The possibility that a previous eon had left a detectable fingerprint in our sky, that the universe before ours had written something into the initial conditions of our own, felt like the kind of discovery that changes everything. And then the rebuttals arrived, within weeks, from multiple independent groups of researchers who had read the paper carefully and asked a simple but devastating question. Had Penrose and Gurdzadian looked at enough patterns in the data that at least one pattern was essentially guaranteed to look significant? This is the look elsewhere effect, and it is one of the most quietly lethal concepts in the practice of science. The intuition behind it is not complicated, but it takes a moment to settle properly into the mind. Imagine that you flip a coin 100 times and you are searching the results for any remarkable sequence. Not a specific sequence you predicted in advance, but any sequence at all that looks unusual. You will almost certainly find one. You might find 7 heads in a row somewhere in the middle of the run. Yes, if you had predicted before you started flipping that heads would appear exactly 7 times consecutively at exactly that position in the sequence, the odds against it would be staggering. But you did not predict that. You searched through every possible pattern in the data until you found something that looked unlikely, and then you declared the unlikely thing as evidence of something meaningful. The problem is that with enough searches, with enough hypotheses tested against the same data, the probability of finding something that looks like a signal in pure noise approaches certainty. It approaches one. You are not discovering structure. You are discovering the inevitable consequence of looking long enough. When independent research groups generated simulated CMB maps that contained no circles, no Hawking points, no signal of any kind, just the statistical properties of random noise that matched the known characteristics of the real data. They found just as many of those circular patterns as Penrose and Gozadjian had found in the actual sky. The circles were there in the simulations. They were there in abundance. And that means they carry no information. They are the coin landing on heads 7 times in a row somewhere inside 100 flips. The pattern is real in the sense that the pixels exist and the temperature values are what they are. But the pattern does not mean anything, because the same pattern appears just as readily when the underlying reality contains nothing at all to find. The honest answer is that his strongest evidence had been seriously undermined. Not destroyed, not conclusively refuted, but wounded in a way that was difficult to dismiss or minimize. The circles were still in the real data, but they were also in data that had been generated by a computer with nothing in it except random noise. And that equivalence is precisely the kind of result that keeps a theory from advancing past the threshold of speculation. But Penrose did not abandon the theory. In 2018, he published again, using a different approach entirely, not searching for circular rings, but analyzing temperature gradients at specific points in the sky in a way he argued was statistically cleaner. And the results from that analysis were harder to set aside. The 2018 analysis worked differently from the beginning. Rather than searching the CMB for circular rings, Penrose examined specific points in the sky and measured the temperature gradients radiating outward from them, the rate at which temperature changes as you move away from a particular location. And then he compared those gradients, point by point, against 1,000 simulated universes, each one generated to have exactly the same statistical properties as the real CMB, each one a synthetic sky built from the same physics, the same noise characteristics, the same fundamental structure. You can think of those simulations as 1,000 alternate realities, not universes with different laws of physics or exotic matter, but universes where the underlying cosmology is exactly the same as ours, where the Big Bang produced the same distribution of temperatures and densities, where nothing from a previous eon has left any mark at all. 1,000 chances for the real data to look ordinary. 1,000 chances for the signal Penrose was pointing at to dissolve into the background the way the Hawking point circles had dissolved. Not a single one of them matched what the real sky showed. The temperature gradients in the actual CMB were higher than every simulated universe in the comparison set. Not slightly higher, not within the range of plausible fluctuation, but an order of magnitude higher. An order of magnitude means 10 times. It means that if you lined up the simulations from lowest gradient to highest, the real data would stand apart from all of them the way a lit match stands apart from a pile of unlit ones. And this was not the result of searching for patterns in hindsight. The methodology specified what it was looking for before looking. Yet the statistical test was defined in advance. The specific criticism that had dismantled the Hawking points, that the researchers had looked at enough different patterns that one was bound to look significant, was the exact criticism Penrose had built the 2018 approach to address. This is what the edge of knowledge actually looks like. Not certainty, not refutation, something in between, where the results are real and the objections are real, and neither side has fully overpowered the other. The signal was harder to set aside than before. Other researchers found problems with elements of the statistical methodology. The debate continued in the literature, which is the honest thing to say. But the numbers from 2018 did not collapse, the way the circles had collapsed. And that distinction matters. And yet, even granting Penrose everything, even accepting that the temperature gradient result is exactly as strong as he claims, the evidence was still his. One man, one theory, one set of papers operating at the disputed edge of what the data can support. The most natural question to ask at this point is a simple one. If something is genuinely wrong with our understanding of cosmic origins, what would independent evidence look like? Not evidence that Penrose found, not evidence connected to conformal cyclic cosmology at all. Evidence from somewhere else entirely, produced by a completely different instrument looking for completely different things, that arrives at the same uncomfortable conclusion, that the universe we observe does not match the universe the Standard Model predicts. The James Webb Space Telescope, launched in December of 2021, folded inside a rocket like something origami and enormous at once, carrying a mirror 6.5 meters across and instruments capable of resolving infrared light from the earliest epochs of cosmic history. It was not built to test Penrose's theory. It was built to see further back in time than any observatory before it, to look at the universe when it was young and ask what was there. The first deep field image it returned, a patch of sky smaller than a grain of sand held at arm's length, contained thousands of galaxies, some of them so distant that the light had been traveling since the universe was a few 100 million years old. And some of those galaxies should not have been there. The Standard Model of galaxy formation, the model built on decades of observation, computational simulation, and theoretical physics, makes specific predictions about what the early universe looked like. In the first few 100 million years after the Big Bang, matter was still assembling itself. Gas clouds were collapsing under gravity. The first stars were only beginning to ignite. Galaxies, as we recognize them, with hundreds of billions of stars and the complex architecture of spiral arms and galactic bulges, required time to build. Not just a little time. The mathematics of gravitational collapse and stellar formation and hierarchical structure growth demanded enormous spans of time, accumulated accretion, galaxy after galaxy, merging and growing across billions of years. What Webb found in February of 2023 was 6 galaxies sitting at roughly 500 million years after the Big Bang, each one between 10 and 100 times more massive than the Standard Model allowed for at that age. The researchers who published the result called them, in their press materials, universe breakers. That nickname was not hyperbole chosen for effect. It was a precise description of what the galaxies appeared to do to the theoretical framework they were supposed to inhabit. Finding a galaxy of that mass at 500 million years is something like walking into a forest that was planted yesterday and finding a fully grown oak tree at the center of it. Not a sapling that grew unusually fast, not an adolescent tree that might be explained by favorable conditions, but a tree with deep roots and a wide canopy and rings inside its trunk that record centuries of growth, standing in soil that has only existed since last Tuesday. The biology does not permit it. The timeline does not accommodate it. And yet, there it is. Some of those 6 galaxies were revisited by follow-up studies, and their mass estimates were revised downward as better data arrived. This is the ordinary process of science. Early measurements get refined, error bars shrink, initial results sometimes soften, but not all 6 of them softened. Several held. And while the scientific community was working through the implications of those galaxies, Webb had already turned its mirror to something older, something further back, and found a galaxy at 280 million years after the Big Bang, a universe so young that the word infancy barely covers it. And the problem with that galaxy was not just its size. In January of 2026, the MOMZ 1014 galaxy was confirmed. Confirmed, not merely observed, not reported as a candidate, but formally established through spectroscopic analysis. At 280 million years after the Big Bang, the light reaching the James Webb Space Telescope had been traveling for 13.5 billion years. The galaxy itself stretched across 1,600 light-years, and embedded in the light from that galaxy, unmistakably, were the chemical signatures of oxygen and nitrogen. Those 2 words, oxygen and nitrogen, may sound like a routine observation, as they sound like the kind of detail that belongs in a footnote rather than a headline. But once you understand how those elements are made and how long the making of them takes, those two words are the most unsettling thing Webb has reported. Because there wasn't enough time. The universe does not manufacture oxygen the way a factory manufactures a product. It cannot simply produce oxygen on demand, given sufficient conditions. The creation of oxygen, and of every element heavier than helium, proceeds through a sequence that cannot be skipped or compressed, a sequence that more closely resembles an assembly line than a chemical reaction, where each stage must complete in full before the next stage can begin, and where no stage can be rushed past a certain point, regardless of what conditions surround it. And the sequence begins with hydrogen. In the cores of the first stars, hydrogen nuclei are fused under pressure and temperature into helium. This is nuclear burning in the most literal sense, mass converted to energy, the mechanism that makes a star shine. But a star that burns only hydrogen will eventually exhaust its fuel, and when it does, the core contracts under its own gravity until the pressure and temperature rise high enough to fuse helium instead. Helium fusion produces carbon. Carbon fusion produces oxygen. Oxygen fusion produces silicon. Silicon fusion produces iron. And iron is where the assembly line stops. Fusing iron does not release energy. It consumes it. Every stage of the sequence from hydrogen to silicon produces energy by combining lighter nuclei into something heavier and more stable. But iron sits at the bottom of the nuclear binding energy curve, meaning there is no arrangement of iron nuclei that releases energy by fusing further. Fusing iron is like trying to extract heat from ice by compressing it harder. The more you push, the more energy you put in, and nothing comes back out. When a massive star builds an iron core, it has reached the end of what nuclear physics will allow it to do. The energy source that has been holding the star up against gravity disappears in under a second. The core collapses. And in that collapse, in the crushing of a stellar core in less than a second, the conditions briefly exist for the most extreme nuclear processes in nature, what physicists call the rapid neutron capture process, the R process, which is responsible for manufacturing gold, platinum, and uranium. All three of those elements were forged in the deaths of massive stars, and then the star explodes, scattering that enriched material across space, where it becomes the raw material from which the next generation of stars will form. That is how the universe builds its chemical complexity, not in a single step, not in a single generation of stars, in sequences, in generations. The first stars, what astronomers call population 3 stars, formed from the primordial gas that existed after the Big Bang, which contained only hydrogen, helium, and trace amounts of lithium. Those stars burned, collapsed, exploded, and seeded their surroundings with heavier elements. The second generation, population 2 stars, formed from that enriched debris and burned and died in turn. Our own sun is a population 1 star, 3rd generation or beyond. And the oxygen in the air of the room you are sitting in was forged inside stars that died before our solar system existed. Working through that sequence, building from pristine hydrogen to detectable oxygen, takes somewhere between 500 million and 1 billion years under the conditions the Standard Model describes for the early universe. That is not a rough estimate. That is the result of detailed stellar evolution modeling built on decades of observations of stars in various evolutionary stages across the galaxy. The processes are understood. The timescales are measured. 500 million years at the very minimum to go from hydrogen and helium to a galaxy with oxygen present in concentrations Webb can detect. NMOMZ14 exists at 280 million years after the Big Bang. Sit with that for a moment. The oxygen is there. The timeline says it cannot be, yet the oxygen is there. To make it physical, if the current age of the universe were compressed to a single calendar year beginning on the 1st of January, 280 million years corresponds to roughly 3.5 days into that year. MOMZ14 is a city of steel skyscrapers and electrical grids and paved highways on a planet that had been cooling from molten rock for less than 2 weeks. Not a settlement, not a foundation, a city with chemistry that required multiple civilizations to build. and the timeline of the universe at that moment did not contain even a single completed civilization's worth of stellar generations. Yet the corrections applied to some of the original 6 universe breakers did not reach this far. Some of those mass estimates softened, yes, and that softening was the ordinary operation of improving measurement. But the mass problem and the chemistry problem are not the same problem, and correcting one does not touch the other. MOMSIT-14 is not primarily a mass anomaly. It is a chemical enrichment anomaly. It is a galaxy that contains products the universe's assembly line had not yet had time to manufacture. The honest response, the one that takes the observation seriously rather than looking for a quick resolution, is to ask what could possibly explain it. And the most frequently offered answer within the standard model framework is that the first stars were radically different from anything we have ever modeled, perhaps far more massive, burning hotter and faster, completing their life cycles in shorter timespans. There are theoretical arguments that stars in the early universe, formed from that pristine hydrogen and helium without the cooling effects of heavier elements, might have grown to enormous sizes. But here the standard model runs into a wall of its own construction. Calculations suggest that stars above 200 to 300 times the mass of the Sun become dynamically unstable, that radiation pressure tears them apart before they can complete their fusion cycles. And the mechanism that might solve the timeline problem runs directly into a separate constraint that caps stellar masses well below what would be needed. That tension does not have a clean resolution yet. It sits in the literature unresolved, growing more acute with each confirmation of early chemical enrichment. And the enrichment problem is not the only timing problem Webb has exposed, because it turns out the universe's chemistry arrived early, and the universe's expansion is also behaving in a way that the model does not predict. And the expansion problem runs deeper than any single galaxy. It runs deeper than any question of how stars form, or how quickly chemistry can accumulate in the early universe. It reaches into the most basic measurement cosmology has ever tried to make. As a measurement that has been refined and checked and refined again across decades of work. And it produces an answer that the universe itself appears to contradict. The Hubble constant is the rate at which the universe expands. Not a rate of change in some distant era, but the current rate, the rate at which space between objects is stretching right now, expressible as a speed per unit of distance. A megaparsec is roughly 3.26 million light years, which is itself a span so enormous that the entire recorded history of human civilization would not occupy a measurable fraction of the time light needs to cross it. And for every megaparsec of distance between two objects, the universe is adding a certain number of kilometers per second to the apparent recession between them. That number is the Hubble constant, and measuring it precisely has been one of the central projects of observational cosmology for the better part of a century. There are 2 ways to measure it, and they disagree. The first method looks backward. When you study the cosmic microwave background radiation, that oldest light, that faint thermal echo of recombination, and you apply the full machinery of standard cosmology to its temperature fluctuations and angular structure, you extract a Hubble constant of 67 kilometers per second per megaparsec. This is not a rough estimate. The Planck satellite produced this number with extraordinary precision, using the most detailed map of the early universe ever constructed, and the number comes out consistently, 67. The second method looks outward from where we are. Astronomers measure the distances to nearby galaxies using Cepheid variable stars, a class of star that pulses with a regularity so precise that its period of oscillation directly encodes its intrinsic luminosity, which means that by watching how bright it appears from Earth and how fast it pulses, you can calculate exactly how far away it is. Build a chain of these measurements outward through the local universe, calibrate carefully at each rung, and you arrive at a Hubble constant of 73 kilometers per second per megaparsec. Not 67, 73. The gap between those 2 numbers is 9%. And if that sounds modest, if it sounds like a rounding difference or an instrumental quirk that better equipment might eventually resolve, consider what 9% means in the context of precision cosmology. And these are not measurements where scientists expect disagreements at that scale. The temperature map of the CMB has been measured to a precision of better than 1 part in 100,000. Cepheid distances have been cross-checked against Type 1a supernovae, against gravitational lensing, against independent geometric methods. 9% is not noise. 9% is a signal. Think of it this way. Imagine you measured the height of a building by running a tape measure up its facade and got one answer. Then you measured the length of its shadow at a known time of day and calculated a different height from basic geometry. Both methods are internally consistent. Both are precise, and they disagree by nearly 1/10 of the result. You would not conclude that one measurement is slightly off, yet you would conclude that something you do not yet understand is at work in the relationship between those two methods. That is the position cosmologists are in. The discrepancy is the same, the confusion is the same, and the building is the universe. For a while, the favored hope was that the Cepheid measurements carried some systematic error, some uncorrected bias introduced by crowding in distant fields, by dust, by calibration chain problems that accumulated rung by rung. The hope was reasonable. Measurement chains are vulnerable to compounding errors, and the telescope used to build them, the Hubble Space Telescope, had known limitations at infrared wavelengths where dust contamination is hardest to correct. So there was a genuine scientific expectation that a better instrument would close the gap. The James Webb Space Telescope arrived with 4 times the angular resolution of Hubble and roughly 10 times its sensitivity at the wavelengths that matter for Cepheid measurement. It could resolve individual stars in crowded galactic fields where Hubble had seen a blur. It could distinguish blended signals that Hubble had been forced to treat as single data points. And when the JWST Cepheid measurements came back in late 2023 and through 2024, they confirmed Hubble's local result. The gap did not close. The local universe, measured with the sharpest instrument humanity has ever pointed at the sky, still expands at 73. The early universe, as described by the CMB, predicts 67. The discrepancy was not a measurement error. It is the universe not agreeing with itself about its own history. Yet the proposals for how to explain this have a particular character. Each one requires adding something new to the standard model, something not yet detected, not yet directly confirmed, introduced specifically to absorb the discrepancy. There is evolving dark energy, in which the cosmological constant is not actually constant, but changes over time in a way that alters the expansion history. There is early dark energy, a form of energy density that existed briefly in the early universe and then dissipated, affecting the sound horizon from which the CMB measurement is derived. There is a non-constant, cosmological constant in the more general sense, where the vacuum energy that drives expansion fluctuates in ways Einstein's original formulation did not anticipate. All of these are formally possible, and none of them has been independently confirmed. Each one represents a patch, a modification inserted where the model tears, and each patch carries its own new questions that the standard model cannot currently answer. And there is one more layer to this, because the cosmic microwave background, the same radiation that anchors the CMB side of the Hubble tension, contains patterns within itself that also should not exist. The radiation is supposed to be uniform, with tiny temperature fluctuations distributed randomly in all directions, reflecting the quantum scale perturbations of the early universe spread isotropically across the sky. But cosmologists analyzing the Planck data found something they called the axis of evil, a preferred direction in the large-scale CMB structure, an alignment of low-order temperature patterns that seems to single out a particular orientation in space. A truly isotropic universe has no preferred direction. Ours apparently does. Then there is the cold spot, an unusually large region in the southern sky where temperatures are measurably lower than the surrounding background, a feature too large and too distinct to dismiss comfortably. And then there is low multipole suppression, a deficit of large-scale temperature variation where the standard model predicts more. These are not the same anomaly. They are separate, unexplained features in the oldest available portrait of the universe, each one sitting in the data, each one generating its own papers, its own debates, its own candidate explanations. One proposed class of explanations reaches toward the idea that our universe is not an isolated system, but one bubble in an infinite foam of adjacent universes, and that during the period of inflation, that rapid early expansion, neighboring bubbles may have brushed against ours, leaving ripples and asymmetries that survived to become visible in the CMB today. That explanation is speculative, but the anomalies that motivate it are not. The universe is not just surprising us with individual objects. It disagrees with itself about its own history, from the scale of a galaxy formed too early to the scale of expansion embedded in space-time itself. The numbers do not fit together the way the model said they would. The impossible galaxies, the impossible chemistry, the expansion rate that splits into two incompatible answers depending on which era you look at. Each of these could, separately, be a problem for a graduate seminar. Together, they begin to feel like symptoms, not of a model that needs minor adjustments, but of a model that is missing something structural. And then, Webb found something that sits outside every category we have: small, red, impossibly bright, and unlike anything else in 13 billion years of recorded cosmic history. What Webb found in those first billion years did not arrive with an announcement or a theory ready to explain it. It arrived as a category error. Hundreds of objects in the earliest epochs of the universe that did not look like galaxies, did not behave like the quasars and active galactic nuclei astronomers had catalogued over decades, and yet were clearly present, clearly bright, and clearly real. Cosmologists started calling them the little red dots, which is a name that sounds almost dismissive until you understand why the color matters and why the brightness is impossible, and why their presence in the data represents something that by every established account of cosmic history simply should not exist. The redness is not incidental. When an object in deep space appears red to an infrared telescope like Webb, there are a limited number of explanations, and the standard ones did not fit here. A galaxy can appear red because it is very old and its star formation has largely ceased, its population of hot blue stars long dead, and only cooler, redder stars surviving. A galaxy can appear red because of dust, which preferentially absorbs shorter wavelengths and lets longer ones through. But the little red dots were compact, far more compact than the galaxies at comparable redshifts, and their spectra showed something else entirely: dense, ionized gas wrapped around a central source so thick that ultraviolet and blue light could not escape, leaving only red and infrared wavelengths to reach Webb's mirror. They were objects inside cocoons, sealed off from the outside universe by walls of heated gas, and only the longest wavelengths of their light could tunnel through. The January 2026 Nature paper from the University of Copenhagen identified what sits at the center of those cocoons. They are black holes, but the number attached to them requires a moment to fully absorb. Each one carries a mass of approximately 10 million times the mass of our Sun. 10 million solar masses in a universe that was only a few 100 million years old when these objects existed. To put that in terms the human brain can hold, the black hole at the center of the Milky Way, Sagittarius A star, which sits at the gravitational heart of a galaxy containing several 100 billion stars and which took the entire lifetime of the galaxy to grow, has a mass of approximately 4 million solar masses. These objects, discovered in a universe so young it had barely finished producing oxygen for the first time, already had more than twice the mass of the black hole that anchors our own galaxy. A universe only a few 100 million years old had produced objects heavier than the black hole that 400 billion stars worth of galactic history created in ours. And there were hundreds of them. The night sky, as seen from a planet inside one of these structures, would be almost unimaginable by terrestrial comparison. You would not be looking at a sparse scattering of distant stars the way you would from Earth on a clear night. The densely packed gas and material surrounding such a black hole would be heated to hundreds of thousands of degrees, radiating energy across every wavelength, filling the local environment with light that outshines the combined output of millions of ordinary stars. A night sky in such a place would have no darkness in it, not the darkness of space between stars, not the soft blackness of a moonless night. Every direction would carry the light of something burning with a violence that has almost no equivalent in the present universe. But what makes the little red dots genuinely impossible under the standard account is not the heat or the luminosity. It is the mass and the time available to reach it. A stellar mass black hole, the kind formed when a very large star exhausts its fuel, collapses, and detonates, begins life at somewhere around 100 solar masses. Some begin smaller. The universe had produced its first stars by around 100 million years after the Big Bang, and those stars lived fast and died in supernovae that might have left behind black hole remnants in that approximate range. From 100 solar masses to 10 million solar masses is a factor of 100,000. The question is how you grow a black hole by a factor of 100,000 in less than a few hundred million years, and the answer the standard model gives is that under normal conditions, you simply cannot. The reason is something called the Eddington limit, and it functions like a tug of war that the infalling matter cannot win past a certain rate. When a black hole pulls surrounding gas and dust toward itself, that material does not fall in cleanly and silently. It accelerates, heats to extreme temperatures, and in doing so emits radiation. That radiation travels outward, and as it does, it exerts pressure on the very material that is trying to fall inward. So the black hole's gravity is pulling matter down, and the radiation produced by that infalling matter is pushing new material back out, and there is a specific accretion rate at which those two forces balance. Trying to feed a black hole faster than the Eddington limit allows is like trying to fill a bathtub while someone on the other side is bailing water out at exactly the rate you are pouring it in. Past a certain input rate, the output keeps pace, and the net gain approaches zero. Growth continues, but it is constrained, and under standard conditions, growing from 100 solar masses to 10 million at Eddington limited rates takes longer than the universe had been alive at the point when these objects were observed. Not slightly longer, considerably longer. Theorists have proposed that black holes can exceed the Eddington limit under specific circumstances, through extremely thick accretion disks that trap the outgoing radiation before it can push infalling material away, or through the frame-dragging effects of a rapidly spinning black hole, where rotation reshapes the geometry of the surrounding spacetime in ways that allow matter to spiral inward faster than the classical picture permits. Super Eddington accretion is not ruled out by physics, but it requires conditions that push against the boundaries of what the early universe could plausibly have provided, and it still does not fully close the gap between 100 solar masses and 10 million in the available time, not for hundreds of objects distributed across the observable sky. The little red dots should not exist, not as a category, not in these numbers, not with these masses, and then they disappear. By the time the universe is about 1 billion years old, they are gone, not transformed into something recognizable, not evolved into a population of objects we can trace forward into the present. They appear in the data of the earliest epochs Webb can reach. They are present across hundreds of independent sightlines, and then somewhere between a few 100 million years and 1 billion years after the Big Bang, they cease to be visible at all. And 3 possible explanations have been proposed for where they went. They grew beyond the cocoon phase, eventually blowing away their surrounding gas and becoming the conventional quasars and galactic nuclei that later epoch astronomy has catalogued for decades. They merged with surrounding material and became the seeds of the enormous galaxies we observe forming in the subsequent billion years. Or something about their environment changed in a way that ended the specific conditions that made them visible in the first place. None of these explanations has been confirmed. The question of their origin is just as open, because whatever process created 10 million solar mass black holes by the time the universe was only a few 100 million years old is not clearly described by any mechanism the standard model provides. And these objects, with their impossible masses and their sealed cocoons and their brief window of visibility, sit inside the same dataset as the galaxies formed too early. The oxygen present before oxygen had time to form, and the expansion rate that means 2 different things depending on which direction in time you measure it from. So there are 3 doors, in a sense, and theorists have been working behind each of them since these objects first appeared in the data. The first is the one already discussed: super Eddington accretion, matter falling in faster than the classical balance point allows, thick disks trapping outgoing radiation, rapidly spinning black holes reshaping their surrounding spacetime through frame dragging, so that material can spiral inward along paths that standard accretion geometry would not permit. The physics is not impossible, but it requires conditions sustained across a long enough period and in enough separate locations distributed across the observable sky that describing it as an exceptional circumstance begins to feel like a category error. Exceptional circumstances happen occasionally. Exceptional circumstances do not account for hundreds of objects. The second door is something called direct collapse. Under standard stellar formation, a cloud of gas fragmenting under its own gravity will break into smaller and smaller clumps, each of which ignites as a star, and the black holes that eventually form inherit the masses of those individual stars, which caps them, in practice, somewhere around a few hundred solar masses at the very upper end. But if a cloud of gas is massive enough, and the conditions are precisely right, as it is possible, in theory, that the cloud skips the fragmentation stage entirely. No stars form. The gas simply collapses, all at once, into a single object. The result would be a black hole seed anywhere between 10,000 and 100,000 solar masses. Not stellar mass, but not yet the 10 million solar masses of the little red dots, though far closer to that target than any star could produce. The catch is that this process requires the gas to be essentially pristine. Any heavy elements present, carbon, oxygen, the kinds of elements that would have been seeded into the interstellar medium by even a small number of earlier stars, act as cooling agents, allowing the cloud to radiate energy and fragment before collapse can complete. Direct collapse requires a region of space where no previous generation of stars has left any chemical signature at all. Given that the little red dots appear in a universe where, as we have already established, oxygen and nitrogen were apparently being synthesized at implausibly early dates, that particular requirement begins to look difficult to satisfy for hundreds of objects simultaneously. The third door is the most radical: primordial black holes, objects that did not form from collapsing stars at all, but from density fluctuations in the very first instance after the Big Bang, within the first second of the universe's existence, before any star had a chance to form. If regions of the early universe were sufficiently dense, they could have collapsed directly into black holes without going through the nuclear burning stage at all. These would have arrived, essentially, as ready-made seeds, and depending on conditions at the moment of formation, they could have been born already massive, giving them a head start across all of the subsequent accretion that followed. The problem with primordial black holes as an explanation is not that the physics is forbidden. It is that we have no direct evidence they exist in the numbers or the mass ranges that would be needed, and invoking them to explain the little red dots requires conditions in those first fractions of a second that go beyond what any current model predicts without extensive modification. And this is the point where the sheer number of objects starts doing its own work in the argument. If one little red dot existed, or a handful, then exotic origin stories are appropriate. Exceptional objects can have exceptional histories, but the count is not a handful. It is hundreds, distributed across independent sightlines, appearing consistently in the earliest epochs Webb can reach. That kind of uniformity does not suggest a rare accident. It suggests a mechanism, something the early universe was doing systematically, at scale, that our current understanding of structure formation does not describe. Every supermassive black hole sitting quietly at the center of a galaxy today may have once been one of these blazing cocoons. Billions of years of cosmic evolution and what Webb may have found in those compact red signatures scattered across its earliest fields is something like the baby pictures, the images of what these enormous and ancient objects looked like before they grew into the architecture that now underlies the entire visible universe. Sit with that for a moment. Every galaxy with a central black hole, every quasar catalogued across decades of prior observation, each of them, possibly, passing through this brief and violent phase that we had never seen before, because no instrument had ever looked far enough back to find it. But the little red dots vanish by around 1 billion years after the Big Bang. They are gone from the data, not transformed into something we can trace with confidence, but absent. The most likely interpretation is that they grew beyond their cocoon phase, eventually driving away the surrounding gas through the sheer force of their energy output and becoming the conventional quasars and dormant supermassive black holes that later astronomy has long catalogued. They are a missing link in that sense, a transitional form glimpsed briefly before it became something else. But being a missing link does not resolve the timing problem. It deepens it, because if there wasn't enough time to build them, then there certainly wasn't enough time to build them and then evolve them through an additional transition, which means the question of origin presses down even harder. And then, alongside all of this, there is a galaxy called J, a DES-GS-Z 13-1-LA, detected at a redshift of 13, which places it 330 million years after the Big Bang, and it is producing something that, according to everything we understand about that era, it should not be producing at all: a strong signal of Lyman alpha emission, a specific wavelength of ultraviolet light released by hydrogen when electrons drop from their second energy level to their first. The reason this emission should not exist at redshift 13 is straightforward. At that epoch, the universe was still overwhelmingly filled with neutral hydrogen gas, and neutral hydrogen absorbs Lyman alpha photons almost perfectly. A photon produced at that wavelength in a universe saturated with neutral hydrogen would be captured almost immediately, long before it could travel any meaningful distance, let alone cross 13.5 billion years of space to reach a telescope. Kevin Heinlein, one of the researchers involved in analyzing the data, said simply that they should not have found a galaxy like this at all. What they found alongside the emission is what makes it stranger still. Surrounding J, a DES-GS-ZO 13-1-LA, in every direction was a bubble of ionized hydrogen, a region where the gas had already been stripped of its electrons, making it effectively transparent to Lyman alpha radiation. That bubble extended 650,000 light-years in every direction from the galaxy. To make the scale of this physical, the distance between the Milky Way and the Andromeda Galaxy, the nearest large spiral to our own, is roughly 2.5 million light-years. This ionized bubble is more than a quarter of that distance. It carved out of the neutral medium surrounding a single galaxy at 330 million years after the Big Bang. Imagine a single source of light clearing a volume of space larger than most of the distances between galaxies in the local group, in just over 3 centuries of millions of years, in a universe that had barely begun producing the first heavy elements. Reionization, the process by which radiation from the first galaxies and quasars gradually ionized the neutral hydrogen that had dominated the universe since recombination, is generally understood to have been mostly complete by around 1 billion years after the Big Bang. That is the standard picture, a slow, cumulative process, driven by countless sources over hundreds of millions of years, eventually clearing the cosmic fog. And what JADES-GS-Z 13-1-LA implies is that reionization had proceeded far enough, in at least some regions of space, to create a bubble that size by 330 million years, less than a third of the way through the window that the standard model assigns to the entire reionization epoch. Either this galaxy was producing ionizing radiation at a rate that strains any reasonable estimate of what early galaxies were capable of, or reionization as a process began earlier or proceeded faster than any current model predicts. The emission shouldn't exist. The bubble shouldn't be that large. And yet, the data is what it is. What becomes difficult to ignore at this point in the account is that these are not separate problems. The galaxies formed too quickly. So the heavy elements appeared before the stellar generations required to produce them had time to complete their cycles. The black holes grew to masses that the available time cannot accommodate through any standard mechanism. And now, a galaxy at 330 million years is doing something to the surrounding medium that the entire epoch wasn't supposed to accomplish until hundreds of millions of years later. Each anomaly arrived in the data individually, dressed in its own specific technical language, assignable to its own specific domain of astrophysics. But they are pointing in the same direction. The early universe was far more structured, far more chemically advanced, and far more energetically powerful than the standard model of cosmological evolution predicts, and the convergence of those findings across independent instruments, independent research groups, and independent observational methods is harder to dismiss as coincidence with every new data release. What becomes difficult to ignore at this point is how thoroughly that description applies to everything that came before it as well. The galaxy too massive for its age at 500 million years, the black holes growing beyond what the available time could accommodate through any known mechanism, the chemical signatures of oxygen and nitrogen in a universe that hadn't run enough stellar generations to produce them, the ionized bubble carved around a single source at 330 million years, when the entire process of reionization wasn't supposed to reach that scale for hundreds of millions of years more, the Hubble tension, her persistent across every cross-check and recalibration, telling us that two precise and independent measurements of the same expanding universe are arriving at numbers that genuinely do not agree. These arrived in the data as separate findings, framed in the technical vocabulary of separate subfields, published in separate journals by separate teams. But they are not separate problems. They are the same problem, stated repeatedly in different languages. And then there is the big wheel galaxy. It was identified in JWST imaging within the first 2 billion years of cosmic history, a period when the universe was roughly 15% of its current age. And it was a spiral, not a rough approximation of one, not a protospiral in the early stages of assembling its geometry, but a pristine, organized, a clearly defined spiral galaxy with arms and structure that would be unremarkable if found in the present epoch. Ivo Labbé, from the University of Cambridge, described it as entirely unexpected, and the phrase carries more weight than it might initially seem. Spiral galaxies are not the default state of matter after a Big Bang. They are the result of a long process of gravitational settling, of collisions and mergers exhausting themselves, of gas cooling and redistributing across stable orbits, of the violent and chaotic early universe gradually calming into something ordered enough that rotation can dominate over turbulence. A spiral galaxy is, in that sense, a record of time. It is the shape that matter takes when it has been through enough. Finding one at 15% of the universe's current age is something like finding a carefully organized library in a building that is still under construction, not just incomplete, but still in the phase where the walls are being poured, where the scaffolding hasn't come down, where the dust of assembly hasn't settled. The organization shouldn't be there. The conditions that produce organization hadn't finished running. And yet, the spiral structure existed, fully formed, rotating quietly in a universe that had barely begun. That phrase, shouldn't exist, keeps appearing in the data. It appeared with the massive galaxies. It appeared with the black holes. It appeared with the Lyman alpha emission at 330 million years. It appears again with the big wheel galaxy's spiral arms. The standard model is not producing one or two results it didn't predict. It is producing a consistent pattern of structure that is, in every case, too mature for the age of the system producing it. The early universe, in JWST's data, reads as if it were optimized for rapid structure formation, as if the conditions at the beginning had been configured, in some way we do not yet understand, to produce organized complexity far sooner than a universe emerging fresh from a singularity has any right to do. Yet this is not the first time that pattern has appeared in science. The history of cosmology, and of physics more broadly, has a recurring shape. A model works, predictions are made, and then anomalies begin arriving at the edges. At first, they are small enough to be assigned to measurement error, to incomplete data, to unknown variables. Then they persist through better measurements. Then they accumulate until the model is not explaining the universe, but rather explaining why the universe keeps failing to match the model. Ptolemy's geocentric cosmology was not simply wrong from the beginning. It was a genuine and sophisticated mathematical framework that matched observation well enough to survive for over 1,000 years. But as instruments improved and data accumulated, the model required corrections, as it required circles rolling on circles, adjustments layered on adjustments, each one locally reasonable and each one making the underlying framework slightly more elaborate. Those corrections are called epicycles, and the word has passed into the language as a general description of what happens when you try to save a model that is quietly failing. Copernicus did not disprove the geocentric model with a single observation. the geocentric model disproved itself gradually through the accumulation of epicycles that were each individually defensible and collectively unsustainable. Newton faced the same structure 2 centuries later, from the other side. His mechanics were among the most successful predictive frameworks in the history of science, tested against everything from falling objects to the motion of planets, and they worked to extraordinary precision. But Mercury's orbit didn't quite behave as Newton predicted. The perihelion, the point in Mercury's orbit closest to the Sun, precessed at a rate that Newtonian mechanics couldn't fully account for. The discrepancy was small. It was not, by itself, a crisis. It was an anomaly, dressed in its own specific technical language, assignable to its own specific domain. Einstein's general relativity resolved it not by patching the Newtonian framework, but by replacing the underlying description of what space and time actually are. The anomaly had been pointing toward a deeper structure the entire time. JWST has been operating for over 3 years now, and with each release of new data, the list of things the early universe was not supposed to do has grown longer. The proposed fixes, evolving dark energy, modified initial conditions, early dark energy models, adjustments to the timing of ionization, are individually plausible and collectively beginning to resemble a familiar architecture. None of what JWST has found proves Penrose's cyclic cosmology, and it would be a misrepresentation of the science to suggest otherwise. But the accumulation of anomalies across independent instruments and independent teams and independent methods suggests that something fundamental may be missing from the standard picture of what the Big Bang was and what it produced. And when you ask what kind of prior state could explain a universe that arrives already configured for rapid structure formation, already seeded with the conditions for fast chemistry and early organization, ESA Penrose's framework does something the standard model does not. It offers an answer. The Big Bang, in his account, is not a beginning, it is a transition, and the structure we are finding in the earliest epochs of our universe may not be the universe generating complexity faster than it should. It may be complexity that was already there, carried forward from something that ended before our clocks started running. To understand how that inheritance would actually work, what the mathematics of transition between eons requires, and what signatures it would leave in the data we already have, we need to go back to Penrose, and to what his theory actually claims about the geometry of that crossing. So let's actually follow Penrose's argument where it leads, not in outline, but in detail, because the detail is what separates a philosophical preference from a physical claim. The standard objection to cyclic cosmology is that it requires a transition between states that don't seem capable of being the same thing. You have, at the end of an eon, an infinite cold void, and you have, at the beginning of the next, a hot dense point of unimaginable energy. And the gap between those two descriptions sounds like it makes the theory self-defeating before it begins. But Penrose's answer to that objection is precise and mathematical, and it rests on a feature of the universe that only becomes relevant when you think carefully about what the final state actually contains. The end state, in his model, is not darkness in the ordinary sense. What remains, and after the black holes have finished evaporating and every massive particle has completed whatever decay it was destined for, is not nothing. It is a universe of photons, massless particles traveling in every direction through an endlessly expanding space. And the critical fact about photons is this. From a photon's perspective, it is emitted and absorbed in the same instant, even if from our perspective, it travels for billions of years. A photon crossing the observable universe experiences zero elapsed time. This is not poetic language. This is a direct consequence of special relativity, which tells us that the faster a clock moves, the slower it runs, and that a clock traveling at the speed of light runs at exactly the rate of zero. When the entire universe consists of nothing but photons, there is no clock anywhere. There is no ruler anywhere. There is nothing to measure distance with, and nothing to measure duration with. And when there is no clock and no ruler, there is no difference between the universe being incomprehensibly large and the universe being incomprehensibly small. Size has ceased to be a physical quantity, and that is precisely when the conformal transformation becomes possible. Conformal geometry preserves angles and local relationships, while treating scale as irrelevant. It is, in a precise technical sense, the geometry that applies when only massless particles exist. The infinite cold endpoint of one eon, described in conformal terms, is mathematically indistinguishable from the hot, dense, compressed beginning of the next. Penrose is not saying they feel the same or seem the same or are metaphorically similar, and he is saying they are the same, that the conformal structure mapping one onto the other is an exact equivalence, the kind of equivalence that appears in pure mathematics, when two expressions that look completely unlike each other turn out to be the same object written in different languages. But this requires something that has not yet been confirmed in any laboratory on Earth. It requires that massive particles eventually decay. Protons, specifically. The proton has been remarkably resistant to experimental efforts to catch it disintegrating. The current lower bound on its lifetime, derived from the Super Kamiokande detector in Japan and other experiments involving enormous tanks of purified water, watched by sensitive photomultiplier tubes for decades, is approximately 10 to the power of 34 years. And that number is already so far beyond the current age of the universe that writing it as a comparison barely helps. The universe is roughly 10 billion years old, which is 10 to the power of 10. The experimental lower bound on proton decay is 10 to the power of 34. That is 24 orders of magnitude larger, a factor of 100 trillion trillion. And yet, that number is nowhere near sufficient for what Penrose needs. His model requires proton decay to occur somewhere in the range of 10 to the power of 40 to 10 to the power of 50 years. We would never detect it in any laboratory we are capable of building, because the rate is so slow that even filling the entire observable universe with detector material and waiting the age of the universe would yield essentially no signal. But undetected is not the same as forbidden. Nothing in the standard model of particle physics prohibits proton decay. Most of its extensions, including grand unified theories, actively predict it. The question is not whether it happens. The question is when. And the black holes. The evaporation time for a black hole of stellar mass is already beyond imagination. For the supermassive black holes that sit at the centers of galaxies, objects of 1 billion solar masses or more, the evaporation time via Hawking radiation is approximately 10 to the power of 100 years. Write A1 followed by 100 zeros. The current age of the universe, written in years, is a 1 followed by 10 zeros. The ratio between those two numbers is itself a 1, followed by 90 zeros. Yet if you tried to count to 10 to the 100th power at one number per second, you would need a span of time that makes the current age of the universe look like a single heartbeat, nested inside an endless afternoon that has no evening. This is not a large number in the way that 1 million or 1 billion is large. It is a number that breaks the ordinary intuition of scale completely and requires you to simply accept that it represents a duration for which no analogy is fully adequate. And yet, across that incomprehensible span, the universe would not be empty in the way we usually picture emptiness. Space would continue expanding. What remained would be occasional photons, each one stretched by the expansion of space to wavelengths longer than the size of entire galaxies. Electromagnetic waves so elongated that the distance between one crest and the next would dwarf everything that has ever existed in our visible universe. There would be no light in any sense that any living thing has ever experienced. There would only be those vast, slow oscillations moving through a void that has forgotten everything it once contained. And that is the state that, in Penrose's account, becomes the next beginning. Not because time ends, because time ceases to be measurable. And a universe in which time cannot be measured is, conformally speaking, identical to a universe in which time has not yet started. But even granting all of that, the proton decay, the evaporation, at the photon endpoint, you are still left with a problem that every cyclic cosmology has to answer. Why does each eon start in a state of low entropy? The second law of thermodynamics insists that entropy increases. And if universes cycle endlessly, why doesn't the disorder from one eon simply propagate forward, producing a successor that begins already degraded, already tangled, already closer to thermal death than its predecessor? Penrose's answer to this is what he calls the Weyl curvature hypothesis, and it is, in its way, the most elegant part of the entire framework. In general relativity, the curvature of spacetime can be decomposed into two components. One is the Ricci curvature, which is directly associated with the presence of matter and energy. It describes how mass-energy warps space in its immediate vicinity. The other is the Weyl curvature, which describes tidal effects, the way gravity stretches and squeezes objects, the way the gravitational field varies from one side of a falling body to the other, the way the geometry of spacetime twists independently of local matter. Near a black hole, Weyl curvature is enormous. The tidal forces at the event horizon of a stellar mass black hole would pull a human being into a thin thread of particles in a fraction of a second. That is Weyl curvature made visceral. But at the Big Bang, in the hot, dense, smooth beginning that the CMB testifies to, the Weyl curvature was essentially zero. The universe was, in its initial state, extraordinarily smooth, almost perfectly uniform. And Penrose proposes that this is not a coincidence and not a fine-tuning problem, requiring an explanation external to the physics. He proposes it as a boundary condition. The Weyl curvature tensor is constrained to zero at each Big Bang, and this is what defines the low entropy starting point of every eon. Entropy, in his account, is not just about the distribution of matter and energy. It is about the geometry of spacetime itself, and specifically about the degree to which that geometry has become tangled and inhomogeneous through gravitational clumping. The black hole era is the peak of gravitational entropy, Weyl curvature at its maximum. Every remnant of structure collapsed into the most extreme distortions of spacetime the universe can produce. The conformal transition resets that to zero, not by magic, yet by the mathematical fact that the conformally transformed endpoint, the photon-only universe, carries no Weyl curvature into the new beginning. The reset is built into the geometry of the transition itself. The honest objections to this framework deserve the same attention. Proton decay has not been observed, and it is possible, though considered unlikely by most particle physicists, that protons are genuinely stable. Black hole evaporation, while theoretically robust, has never been directly confirmed for any black hole of any size, because the radiation from astrophysically relevant black holes is far too faint to detect against the background of the cosmic microwave background. And the information paradox, the question of whether the quantum information that fell into a black hole is destroyed in the singularity or somehow encoded in the Hawking radiation that eventually carries the black hole's mass back into the universe, remains one of the deepest unresolved problems in theoretical physics. Penrose's own position is that information does survive, encoded in the outgoing radiation, carried forward into the next eon. But this is not a settled claim. It is a proposed resolution to a problem that has occupied some of the finest physicists alive for 50 years without producing a consensus answer. What is worth recognizing, though, is that Penrose did not arrive at this framework by deciding he wanted cyclic cosmology and then constructing mathematics to support it. And he arrived at it by following the geometry. And the remarkable thing, the thing that this story has not yet reached, is that working from completely different starting points, using completely different mathematical languages, other researchers building on string theory and on loop quantum gravity have found themselves at a door that looks, from the outside, strikingly similar to the one Penrose found from the other side. What Penrose found from the mathematics of conformal geometry, Paul Steinhardt and Neil Turok found from a completely different direction in 2001, working not from topology and differential geometry, but from the deep machinery of string theory. Their model, the ekpyrotic model, from the Greek word for conflagration, does not begin with a dying universe full of photons. And it begins with a question about the geometry of space itself, at a level far below anything we can observe, and it arrives somewhere that should, by rights, have nothing to do with Penrose's work. The fact that it does is the thing worth attending to. String theory, when pushed to its natural mathematical conclusions, does not describe a universe with 3 dimensions of space and 1 of time. It describes a universe with additional dimensions, dimensions that are either curled up at scales far too small to detect directly or extended across what theorists call the bulk, a higher dimensional space in which our 4-dimensional universe is a surface, a membrane, a brain, floating like a film of oil on water. Steinhardt and Turok took this seriously not as a curiosity, but as a physical model, and they asked what would happen if our brain were not alone in the bulk, if there were another brain, parallel to ours, separated by a gap in the extra dimension, drawn toward us by a potential, by something like gravity operating across that gap, then eventually, the two brains would collide. Imagine two vast flat membranes, each one an entire universe in its own right, floating in a higher dimensional space that contains them both, the way water contains two sheets of paper floating near each other. Each membrane has its own distances, its own stars, its own history. They drift closer across the extra dimension, and when they collide, when these two four-dimensional surfaces slam into each other across the bulk, the energy of that collision, which is effectively infinite from the perspective of the particles on either surface, appears from inside each brain as an explosive, uniform surge of energy and heat filling all of space simultaneously. It appears, in other words, exactly as the Big Bang appears from inside our universe. Not a creation from nothing, a collision, an energy transfer from a higher dimensional impact that our three-dimensional instruments register as a beginning because we have no way of looking into the extra dimension and seeing the approaching brain before the moment of contact. After the collision, the two brains rebound. They separate back across the bulk. The universe we are in, our brain, expands, cools, forms structure, produces galaxies and stars and the full history that JWST is now photographing. And then, slowly, over timescales that dwarf ordinary cosmological time, the potential draws the brains together again. Another collision, another Big Bang, from the perspective of anything living on either surface. Not because matter cycles through death and rebirth, as Penrose requires, but because the geometry of a higher dimensional space produces the collision as a natural, repeating consequence of how brains move through the bulk. The cycle is not built into entropy. It is built into the topology of the extra-dimensional geometry. The mathematics is entirely different from Penrose's. The physical picture is entirely different. And yet, the conclusion is the same. Our Big Bang was not an absolute beginning. It was a transition. The universe existed in some form before the moment we call the beginning, and it will exist in some form after the moment we will eventually call the end. This is not one man's idea. This is a pattern emerging from completely independent branches of physics, and that is usually how revolutions begin, not with a single breakthrough, but with convergence. Loop quantum cosmology arrives at this conclusion by a third route entirely, one that does not require extra dimensions, does not require brains, and does not require conformal geometry. It requires only one step beyond the standard framework, the recognition that if quantum mechanics governs everything else in the universe, it must eventually govern space itself. In general relativity, space is smooth and continuous. It can be curved, it can expand, it can contract, but it has no minimum unit. Loop quantum gravity challenges this directly, proposing that space, at the scale of the Planck length, a scale so small that writing it out numerically would be meaningless to any physical intuition, is not continuous at all. It is quantized. It comes in discrete, indivisible units, the way light comes in photons. Space at the deepest level has a grain, and that single assumption changes everything about what happens at the Big Bang. In classical general relativity, when you run the equations backward in time, the universe contracts toward a singularity, a point of infinite density, infinite curvature, where the equations break down and physics stops. This is the wall at the beginning of time. Loop quantum cosmology runs the same equations backward, but with quantized space, and what it finds is that the contraction cannot continue past the point at which space reaches its minimum grain size. Space cannot be compressed further than its smallest possible unit, any more than a string can be divided past its individual fibers. When the universe contracts to that limit, it bounces. The singular wall is replaced by a quantum mechanical rebound, a big bounce, and the universe that existed before the bounce, contracting toward its minimum, becomes the universe that now expands on the other side. What we experience as the Big Bang, in this picture, is the moment of maximum compression before the bounce. not a creation, a reversal. These three frameworks, conformal cyclic cosmology, the ekpyrotic model, loop quantum cosmology, were each developed by researchers working on different problems, using different tools, in dialogue with different communities in physics. None of them set out to confirm the others. Penrose was following the implications of entropy and conformal geometry. Steinhardt and Turok were following the implications of brane dynamics in string theory. The Loop Quantum Cosmology program was following the implications of quantizing gravity. It is as if three different expeditions, setting out from three different continents without any knowledge of each other, each arrived independently at the same island. That kind of convergence does not prove anything, but it is exactly the kind of signal that serious physicists recognize as worth taking seriously. When the same conclusion appears in frameworks that share no assumptions, the conclusion tends to be pointing at something real. There is another consequence of any cyclic model that bears attention here, because it addresses one of the deepest puzzles the standard model has never fully resolved: the arrow of time. The second law of thermodynamics says that entropy increases, that the universe moves from order to disorder, from low entropy to high entropy, and not in reverse. This is not controversial. The question that has never been satisfactorily answered is why the universe started in such a low entropy state in the first place. Why was the Big Bang so smooth, so uniform, so ordered, when the overwhelming majority of possible initial conditions would have produced a chaotic, high-entropy mess? The standard answer is essentially to assert it as a special initial condition and move on. But in any cyclic framework, a low-entropy beginning is not a miraculous exception. It is what every cycle produces by construction. The conformal transition resets the Weyl curvature to zero. The brane collision distributes energy with extraordinary uniformity. The quantum bounce reflects the geometry through its minimum. Each of these mechanisms, from its own direction, naturally produces the smooth, a low-entropy beginning that the standard model can only postulate. The arrow of time in a cyclic universe does not need an explanation from outside the physics. It is the physics. And this is where the James Webb Space Telescope becomes something more than an extraordinarily powerful camera. Every observation it makes at extreme redshift, every galaxy too massive, every black hole too large, every chemical signature that appeared too early, is a probe of conditions at the very earliest moments of cosmic structure formation, which is precisely the regime where quantum gravitational corrections, if they exist, would have left their fingerprints. General relativity, extended all the way back to the Big Bang, predicts specific patterns in how structure forms and how matter is distributed. If the Big Bang was instead a bounce, or a brane collision, or a conformal transition, the initial conditions would carry subtle but detectable differences, slight modifications to the power spectrum of early fluctuations, anomalies in how the largest structures are distributed, hints that something seeded the universe's early development in a way that a pure singularity would not have produced. The JWST anomalies may not be puzzles within the standard model. They may be the first observational hints that quantum gravity, at the moment of the bounce, or the collision, or the transition, left traces that 10 billion years of cosmic expansion have not entirely erased. The honest position is that none of this is confirmed. But time, in any of these frameworks, does not have a beginning any more than a circle has a starting point. Yet you can trace it in either direction and never reach an edge. And that, the possibility that we are sitting inside a structure with no edge, no origin, no first moment, is the thought that has been building towards something the mathematics alone cannot answer. Let's think about what it would mean if Penrose's model turned out to be correct, not as a matter of abstract physics, but as a matter of what you are, physically, right now, sitting wherever you are sitting. The hydrogen in your cells is the oldest material in the universe. It was forged in the first 3 minutes after the Big Bang, when temperatures were high enough to fuse protons into the lightest elements, and it has been incorporated into countless structures since: nebulae, protostellar clouds, oceans, organisms, before arriving, at this moment, inside you. At that much is standard cosmology. But if Penrose is correct, if cyclic cosmology is correct, if the Big Bang was a transition rather than a beginning, then the hydrogen in your cells was not created in this Big Bang. It has been through countless previous ones. The same proton, or its constituent pieces, cycling through eon after eon, through the deep cooling and the conformal transition, through the next ignition and the next expansion, through billions of years of stellar nucleosynthesis and galactic evolution, arriving here, now, as part of you, not as a metaphor, as a literal description of where the matter in your body has been. The carbon in your bones may have been forged in a star that burned and collapsed in a universe we will never be able to reach or observe, in an eon separated from ours by a transition that erased all information about what came before. The oxygen in your lungs may have cycled through a number of previous eons we have no way to count, not thousands, not millions, but potentially an infinite regress of cosmic deaths and rebirths, each one resetting the geometry, each one scattering the same fundamental matter into a new universe to be assembled and dissolved again. The forms change continuously. Stars become dust, and dust becomes stars, and stars become black holes that eventually evaporate across timescales so vast that even the word timescale feels inadequate, and the photons that remain carry the geometry forward into the next beginning. But the being persists. It is never created from nothing. It is never destroyed into nothing. It simply transforms, endlessly, and through every scale from the subatomic to the cosmological. That is not a spiritual claim. That is what the physics implies if the cyclic picture is correct. And there is something else worth dwelling on here, which is the specific moment in history when you happen to be alive. Not the moment in cosmic history, though you are living at roughly 8 billion years into the current eon's stellar formation era, which is itself remarkable. The moment in human history. You happen to be alive at the precise point when humanity built a telescope powerful enough to peer back to within 280 million years of a Big Bang that might not have been the beginning. The James Webb Space Telescope has been returning data for just a few years, and discoveries are arriving every few weeks. Not every few years, every few weeks. MOMZ14 confirmed at the very frontier of the observable universe. Little red dots identified in their hundreds. Chemical signatures that should not exist. Spiral galaxies organized with a patience the universe had not yet earned. Each observation lands, and then, before the field has fully absorbed it, another one arrives. The Standard Model is under more observational pressure than at any point in its 50-year history, and the pressure is increasing, not stabilizing. Roger Penrose is 93 years old. He proved that black holes were real when the physics community was still reluctant to believe Einstein's equations meant what they said. He spent the decades since building, piece by piece, a cosmological framework in which the universe has no beginning and no end, in which what we call the Big Bang is a seam and a transition between one vast chapter and the next. He is still arguing for it. He is still publishing. He is still presenting at conferences, still responding to critics, still refining the mathematics with the same topological intuition that made the singularity theorems possible. Whether he is right or wrong, the persistence itself is worth something. The man who spent his career proving that singularities are real is now arguing that the most famous singularity of all, the one at the beginning of time, may not have been a beginning at all. The anomalies have accumulated into something that demands a reckoning. The little red dots with black holes too large for the universe's age. The universe breakers, those galaxies at 500 million years with masses the Standard Model cannot accommodate. The rapid chemical enrichment that placed oxygen in a galaxy at 280 million years, before the stellar generations needed to produce it had completed their cycles. The Hubble tension, a 9% disagreement between two independent measurement methods that has only deepened as the instruments improved. Penrose's Hawking points, those circular low-variance rings in the microwave background that he reads as echoes of black hole deaths in a previous eon. None of these anomalies, taken individually, is necessarily fatal to the standard picture, but they arrived together. They arrived at the same time, and they arrived because we finally built something capable of seeing clearly enough to find them. We may be approaching the moment when the question resolves. It is possible, genuinely possible, that the next several years of James Webb observations, combined with the Euclid Space Telescope mapping large-scale structure, combined with future measurements of the cosmic microwave background at higher resolution, will produce data that simply cannot be reconciled with a singular beginning, data that points unmistakably toward initial conditions that carry the fingerprints of something prior. It is equally possible that the anomalies will resolve within the standard model one by one, as better measurements sharpen our understanding of stellar physics and early galaxy formation. We might discover that the Big Bang really was the beginning, that the standard model is correct, that the anomalies were misunderstandings rather than messages. Either way, we will know, within decades, perhaps within years, we will have an answer to a question that has been present in human consciousness since the first person looked up at the night sky and asked, what was there before all of this? And as you go about your life, as you deal with the ordinary concerns of ordinary days, there is some comfort, or at least some perspective, in holding this thought, that you are living through an extraordinary time, that the atoms assembling you have potentially traveled through depths of time we cannot measure, and that the universe around you, all of it, everything that has ever existed, may be not a single story with a beginning and an end, but an eternal dance of creation and destruction, so vast and so patient, that the whole of human civilization so far occupies less than a breath of it. And here is the thing that stays with you. Once you have sat with all of it long enough, not the anomalies, not the tension between the numbers. What stays with you is something quieter than that. The simple fact that you are here, in this moment, alive during the brief window in human history when we built something capable of asking these questions and receiving actual answers. The most powerful telescope ever built has been pointed at the oldest light in the universe, and what it found was not confirmation. What it found was surprise after surprise after surprise, arriving every few weeks, each one a small crack in the picture we thought we had finished drawing. That is not a failure. That is the most honest thing science ever does. It looks carefully enough to discover that it was wrong, and then it looks again. Consider what it means to be a human mind holding this particular thought at this particular moment. The brain doing the holding weighs roughly 3 pounds and runs on something close to 20 watts of power, less than the bulb in a bedside lamp. And yet, it has managed to measure the expansion rate of a universe 13.8 billion years old, to detect the chemical fingerprints of oxygen in a galaxy that formed when the cosmos was less than 3% of its current age, and to ask, seriously and rigorously, whether all of that history might be not a beginning, but a chapter. The vastness is not the point. The vastness has always been there. What is new, what is genuinely extraordinary, is that something inside it learned to look back. If Penrose is right, and we do not know whether he is, and that uncertainty is real and honest, then the 13.8 billion years behind us are not a total. They are an installment. The atoms assembled into you right now have potentially traveled through aeons that no measurement we currently possess can reach, surviving the cold and the dark and the slow dissolution of one universe, passing through whatever the conformal boundary really is, and finding their way into a new configuration in a new cosmos that would look, from the outside, like another Big Bang. Not destruction and then nothing. Destruction and then eventually everything again. That reframe changes what the dark means. The heat death that waits at the far end of this eon. The empty, cold, a quiet void where the last photons drift through infinite space with no destination, stops being a final word when you hold it next to Penrose's model. It becomes, instead, a pause, a held breath, the moment of absolute stillness just before something unimaginable happens again. The universe does not end. It rests. You are going to close your eyes in a few minutes, and everything you are aware of will go dark. And while you sleep, the James Webb Space Telescope will continue its work, pointing at galaxies so distant that the light reaching its mirror left before the Earth existed. And somewhere in that data, there may already be the answer to the oldest question anyone has ever asked. You will not know it tonight, neither will anyone else, but it is there, or it is arriving. And the fact that we are asking at all, that a species that did not exist 100,000 years ago on a planet orbiting an ordinary star in an unremarkable galaxy has built instruments sensitive enough to measure the shape of the universe's first breath, That fact is, in its own quiet way, as extraordinary as anything the telescope has found. So rest with that weight on you, not as a burden, but as a kind of gravity, something that holds you to this moment. You are here. The cosmos is vast and possibly eternal, and you are the part of it that knows.